So we got polar versus nonpolar for compounds, right? And you're right. Yeah, that was loud. Okay, good. So anyway, the point of doing all of that, who cares if we can tell if compounds are polar? Like, that's not an important thing in itself. The important thing is because we want to be able to judge what types of attractive forces are happening between molecules. And in order to do that, we need to know whether the molecules are polar or nonpolar because they have different types of forces by which they get attracted. So this phrase here is the most important thing, and that's what we're going to talk about now. Now that we can say whether things are polar or nonpolar, we can talk about the different kinds of attractive forces. So the first types that we're going to look at are the polar forces, and then we'll look at the nonpolar forces. Polar molecules attract each other in the way that you'd expect, positive and negative attracting. So if you have something like well, let's just take water. So we drew water, and we said that there's a positive on the hydrogen and negative on the oxygen. Okay. So the way that might interact or attract with another water molecule is that the negative part of another water molecule would line up with the positive part of the first one, and you'd get this attraction. Now that is the intermolecular force. That is the polar attractive force, that thing that we drew in green. It is weaker than a covalent bond. But it is still strong enough to hold these things together at a reasonable temperature, like whatever room temperature. Water is a liquid because those forces are strong enough to hold water together. The type of force that this is confusingly called a hydrogen bond. The reason I say that's confusing is it's not a covalent bond. It's an attractive force between molecules, but it's called a hydrogen bond. And it's not a covalent bond. It's not hydrogen bonding with another hydrogen or something. It's this type of force, and it just happens to be called a hydrogen bond or hydrogen bonding. This is the strongest type of intermolecular force. And we can find it whenever molecules contain OH, NH, or FH bonds. So if the polarity in the molecule comes from OH, NH, or FH, then it makes this extra strong connection that we call hydrogen bonding. Otherwise, it's just regular polar attractions. And we can also note here that OH makes the strongest connections. So it's not that an OH bond itself is strong. It's that an OH bond is very polar and can allow these molecules to connect with each other. The way that we can measure this or see it in action is by looking at boiling points. Stronger attractions, stronger intermolecular forces lead to higher boiling points. Why do you think that is? What are we doing to the molecules when we boil them? For what? You're tearing the molecules apart. So when you boil something, you're not breaking the covalent bonds. When you boil water, you still have water. It's just water vapor, right? You're just changing the state. So you're not breaking the covalent bonds. You're breaking the intermolecular forces. You're separating the molecules from each other, spreading them out. So the stronger those intermolecular attractions are, the more energy it takes to boil something. So let's look at three molecules that are about the same size. Because size also affects boiling point. We'll get into that in a little bit. We're going to look at methane, ammonia, and water. Excuse me. And let's look at their molar masses so that we can see the size. And then compare that to compare the boiling points. All right, so the molar mass of CH4 in grams per mole is 16. Ammonia is 17. And water is 18. So about the same size. Even though it looks like there's a trend there, it's a pretty small difference. So we're going to say about the same size. All right, now we can look at the boiling points. The boiling point of methane is minus 161 degrees C. The boiling point of ammonia is minus 33. And the boiling point of water is 100, positive 100. So what this is showing is, even for the same size molecules, as the types of forces change, as the intermolecular forces strengthen, the boiling point goes up. It takes more and more energy to separate these molecules from each other. The one with the very, very low boiling point is methane, which we've already talked about is nonpolar. And then the other two are polar. So having those polar forces present to attract the molecules makes the boiling point get much higher. The stronger those forces are, even for the same size molecules, the harder it is to boil them, to separate them. So that's how the polar attractive forces work. And that's why we spent so much time on that previous part of trying to determine whether or not a molecule is polar. Because if it is polar, then its attractions are going to be much stronger, and it's going to have a much higher boiling point. It's also going to affect how things mix with it, which we'll talk about when we get to solutions in a little bit. So let's now talk about the nonpolar forces. So these are much, much weaker. And the way we've been talking so far, it kind of seems like they shouldn't even exist. So if something's not polar, how does it attract other molecules to it? And we'll talk about why that is. But we know that it does actually happen because, well, like we just said, okay, methane's got a really, really low boiling point, but we can access that. Like that's not like some crazy unimaginable number. It's low, but you can't actually condense methane and have liquid methane. So that tells us that there must be some kind of attractive forces, because if there were no attractive forces at all, you could never have a liquid or a solid of that compound. So anything that can be condensed into a liquid must have some kind of attractive force, even if they're very weak. And the weak nonpolar forces are called dispersion forces. And these are much weaker than the polar forces. What they come from is, if we draw an atom, let's say here's our nucleus. There's a nucleus of an atom, and let's say there's some electrons. We'll call it a helium atom. And so there's going to be 2 electrons around. Now we know they don't actually go in circles, right? They're just in this shell, and they can be at any position in that shell. But depending on where they are, they can actually affect the electrical properties of the atom. So at any given moment, let's say the 2 electrons are exactly opposite of the nucleus. Well, then there's not going to be any polarity in just that one little atom, because everything's balanced out. But let's say in another instant, just like a tiny, tiny fraction of a second, all of a sudden the electrons are both on the same side, because electrons move randomly and they could be on the same side. Well, if they're on the same side, all of a sudden we have a momentary polarity. Like just at that very, very moment, there's a little bit of negative over here and a little bit of positive over here, just because of where the electrons happen to be. Well, as it turns out, as soon as that happens, it affects everything else around it. And all the other electrons and all the other atoms can suddenly line up to like compensate for that. So if that happened, then let's say we've got another one right here. Well, all of a sudden that little bit of negative charge is going to repel those electrons and make those electrons go over on this side too. And now this one has a little bit of a polarity too. Maybe we should draw, like here's our first shell here, okay? The electrons are inside the shell. So as those connect, it starts kind of propagating this chain reaction. It's called an induced dipole, and that's where these forces come from. And so for these forces, since they don't have any special like polarity that controls them or anything, the strength of the forces depends only on the size of the molecule. The more electrons and the bigger the molecule, the more these things can have an effect, and you can actually end up getting relatively strong forces this way. So for example, we said that methane has a very, very low boiling point. But as you keep adding carbons, you actually can get a higher and higher boiling point, to the point of, let's see, if you had the molecule octane, which is C8H18, that's in gasoline. It's the major component of gasoline. That's a liquid, right? You ever just like spray gasoline all over the? Don't do that. But if you did, you'd see that it's a liquid. And that's because when we get up to 8 carbons, those forces end up being strong enough that it can actually become a liquid. And if it keeps going, does anybody know what you get if you take like really, really long chain carbons, like 20 carbons in a chain kind of thing? Does anybody know what those types of materials are? They are waxes, this one, so like a candle. waxes can be solid, actually, because when you get that many carbons, it will actually have enough strength to form a solid. Pure carbon's a little bit different because so there's there's a few forms of pure carbon, but the main ones that we talk about are graphite and diamond. Diamond actually doesn't have intermolecular forces because all the carbons in diamond are covalently bound to each other. So that's like actually a fully covalent structure. That's why it's one reason why it's so strong. Graphite is like in sheets, and the sheets can come apart from each other. So the solid part, it is actually also covalently bound, but then the reason that it is kind of feels like almost a lubricant is that the sheets can shear from one another. But that's a little bit different than this stuff. So the point of this is nonpolar forces are much weaker in general than polar forces, but if the molecule is big enough, they can start being relatively strong as well. So let's think about this and rank some molecules. All right, so here's two molecules in the book, from the book. And we want to know which one would we expect to have the higher boiling point. So this first one is a molecule called butanol. Pretty big molecule here. C4H10O, the formula. And then here's another molecule that has the exact same formula. So it's made of the exact same atoms, but they're going to be connected in a different way. It's called diethyl ether. And the question is, which one has the higher boiling point? All right, so talk within your tables or whoever you can talk to, and come to a decision of which of those two would have the higher boiling point and why. Then I'll ask you for your answers.
This polar. So HC. Hold on, he's gonna fit to this plate. I was but that's
All right, does everybody have a pick? Yeah, we're still thinking about it. All right. Were your groups in agreement, or did you have to have some fights about it?
No, I'm trying to come back to agreement. We're just trying to
figure out.
When something's polar versus something.
Okay. All right. So let's take a poll here. So how many people said that the first one would have the higher boiling point? How many people said the second one would have the higher boiling point? You all didn't decide? All right, so why? What was your reasoning? Okay, so in the H. Okay, anybody else? You're looking at the carbons? What about the carbons?
There's 3 bonds. And all 4 carbons opposed to just 2.
Okay. How does that affect the intermolecular forces then?
Well, my bond, because there's more bond carbons. I forgot, what was the second molecule? What was the name?
Ether.
Okay. So I figured if you're going to boil, it would take more energy or a higher temperature to boil butane as opposed to.
Okay. Would the carbon-carbon bonds break when you boil it? What do you think? Anybody? If you boiled one of those molecules, would the carbon-carbon bonds break or not? Let's generalize it across any chemical compounds. When you boil a compound, do the bonds inside the molecule break? Right. The bonds don't break. The covalent bonds don't break when you change something's state. Remember the chemical versus physical changes? If you're breaking chemical bonds, you're changing the identity of a compound, right? You're changing it physically. Or you're changing it chemically. You're changing it into something else. If you're boiling something, that's a physical change. You're changing something physically. You're just changing its state. So you can't actually, excuse me, you can't destroy the molecule when you boil something. So boiling only separates molecules from each other. It does not break the bonds inside the molecule. But I'm glad you brought that up. Actually, did I turn my microphone back on? Yeah, I did. Okay. I'm glad you brought that up because that's a really, really common thing that people sometimes have issues with when it comes to these kinds of judging boiling points is you want to look at and judge the strength of the bonds in the molecules. But boiling point is not affected by the bonds in the molecules. It's affected by the connections that the molecules have to each other. So whether the molecules can attract each other really well, really strongly or not. So in this particular case, the first one would have the higher boiling point. In fact, let's look at those numbers. Even though they're the exact same size, they have the same types of different atoms. Oops, I flipped my page too early. Okay. The first one's boiling point is 117 degrees C, and the second one is 34.5 degrees C. So big difference in boiling point. And the biggest effect on that here is this polarity difference that we see. We go back up to what we were talking about before. Whenever you have an OH, an NH, or FH bonds, you have this especially strong type of interaction called hydrogen bonding. And so that's what causes that boiling point. The second molecule actually does have a little bit of polarity, even though you can't tell from the way I drew it, because there is like a zigzag to it. So there is like the O does give it a little bit of a polarity, but not enough to make for that strong of a boiling point. All right, let's try another one. Now we're going to look at free molecules. Propane. Isopropyl alcohol, which is rubbing alcohol. Oops, hold on. And propylene glycol. All right, same question. Again, talk in your groups, see if you can come to an agreement, and decide both on which one's the highest, which one's the highest boiling point would you expect, and make sure you have a reason for that. Yeah. You wouldn't be able to tell. It's not a shake. Yeah. All right, got some ideas on this one? How many people said the first one is the highest boiling point? Second one? Third one? Whoa, it's unanimous. All right, why the third one?
What?
Finish chewing, then try again.
It has two of the polar bonds, the OH, just two of them.
Yeah, right. And two of these. Is that what everybody said? Okay. Well, unfortunately, you're all. Oh, you're right. That's right. So.
Forget what I thought. You're all wrong.
Right. I want to make sure that we understand the reasoning for that, though. It's not that those OH bonds are strong. So when I ask you which one has the highest boiling point, and I ask you to explain your answer, make sure, and I think you get it, but make sure that you're saying that you're talking about the attractions between different molecules, not the bonds in that molecule. See the difference there? If you're boiling that, you're not breaking the O and H apart. Those stay together, but the different molecules separate from each other. And having the OH there, or the two OH there's, the two OHs there, gives a particularly good way for these molecules to connect with one another. So you want to always be thinking about how these molecules can interact with each other. If we go back up to, and you could draw it too. So you could draw something like this with the OHs from the propylene glycols from separate molecules like coming in together. It'd be kind of annoying to draw, but you could like draw it out like that. But those are the types of connections that anything with OH or NH bonds can make. And that's why those can hold each other together more strongly than the others. In our other example here, this is also polar. So that will also have those connections, just not as strong of connections. You've probably experienced at least a couple of these molecules before. Propane on the left is the stuff that you have in the big tank that like goes into a grill or something, and that's a gas at room temperature. So that means that its boiling point is much lower than room temperature. The second one is rubbing alcohol, isopropyl alcohol, and that's a liquid at room temperature, but it evaporates pretty quickly, right? And then the third one is propylene glycol, which is actually kind of viscous, like it's a little harder to pour. It's kind of almost has like the consistency of oil, and doesn't really evaporate well at all. It's used in things like antifreeze, so that it doesn't boil, or it doesn't boil when it, even though it says it's called antifreeze because it doesn't freeze, but it also doesn't boil with the high heat of the engine. So having more of those types of connections can attract those molecules to each other better. That's what we're looking at there. Make sense, maybe? A little bit? Okay. All right, so let's talk about other factors besides just boiling point. So how other things are affected by these intermolecular forces. A couple little ones that maybe aren't quite as important, but they mention in the book. Surface tension. So if you have a liquid, you know how when you put like a droplet of water on somewhere, it kind of makes that bead look, that dome look. And that's because those molecules on the surface are pulling each other together. And the stronger the intermolecular forces, the more of a surface tension you're going to have. The weaker the forces, the less of that you're going to have. So if you put a drop of water, you can try this at home sometime. You put a drop of water versus a drop of rubbing alcohol or something less polar, you'll see that the less polar thing spreads out more. It doesn't jump as much, doesn't have as much strength I'm sorry. I'm confused a little bit. Surface tension is if you take a bulk of a sample and you have like the surface of it, how strong is that surface? So like you can float a paper clip on top of water, right? You can't float a paper clip on top of a non-polar substance because it will just fall through because the molecules can't form as tight of a network on the surface because they don't have as strong of intermolecular forces. So same thing like boiling point. The stronger forces, the greater the surface tension. Another one is viscosity. So how quickly something flows is the viscosity. This one can be a little bit tricky because it's often confused with density. And a good way to not confuse yourself about that is oil. So oil, like vegetable oil or any kind of cooking oil, has a pretty high viscosity, right? Like when you pour it, kind of like doesn't pour as quickly as water. But it is less dense than water because the oil floats on top of water. So viscosity isn't density. Viscosity is like how well something flows. And viscosity is a little tricky because it's generally predicted by intermolecular forces. The greater the forces, the thicker something is. So like something like honey or like something with a lot of sugar in it has a lot of those connections together and flows really, really slowly. as opposed to something much lighter. But there's also things that change their viscosity as they flow, like ketchup. I don't know if you've ever noticed ketchup. Has anybody ever used ketchup from a glass bottle? What happens when you pour ketchup from a glass bottle? And then, yeah, so it comes out really slowly, and you can't get it out and can't get it out, and then all of a sudden it goes, and like your whole thing is covered in ketchup, right? And then, yeah, you don't even want this much, and that's because ketchup actually changes its viscosity as it flows. So when it's sitting, it's very, very viscous, so viscous that it doesn't want to do anything. And then as it starts to flow, it actually gets less viscous and less viscous. It's almost like a chain reaction. It gets thinner and thinner as it flows. So once it starts flowing, it flows way faster than you thought it was going to, and that's how you always get way too much ketchup. There's several materials that do that. They don't quite follow the rules, and they're kind of fun that way. Cornstarch and water is another mixture that does that. That if you kind of it's actually the opposite. If you let it sit, it flows, and if you subject it to force, it actually like hardens up. Kind of fun. All right, so then the more important than those for our purposes is mixing, which we're going to call solubility. How well do two things mix together? Do they form a homogeneous mixture or a heterogeneous mixture? That is also dictated by the type of intermolecular force. So let me show you what that might look like. I'm going to draw a bunch of what I'm going to say are oil molecules. So here's our oil. Oil molecules are big, long carbon chains. They're actually capped with some polar stuff, but no OH bonds. So I'm just going to draw oil molecules as like kind of squiggly lines like this. So they're just kind of big carbon chains. And since oil is made mostly of carbon and hydrogen, it is nonpolar. And the types of forces that attract each other, attract the molecules in oil, are dispersion forces. So the forces that are holding these things together are the dispersion forces. So then let's look at water next to it. And water, we know, is held together by hydrogen bond forces. And so I'm going to use red to indicate those. I can try. I had plans to make it like way bigger, but then I got bored and stopped. So let's see if I can just, yeah. Do that. Show a little bit. Just makes my writing look worse. Is that better? So here's our hydrogen bonding polar forces that are connecting the water molecules. You don't have to draw it. Just, I mean, this is on Blackboard, so you can just listen. So the point being that these two samples have different types of forces. The oil is held together by dispersion forces that are actually relatively strong at this point because oil molecules are big. And dispersion forces, the nonpolar forces, are dependent on molecular size. So these big oil molecules are attracted by these dispersion forces fairly strong. Then water is a very small molecule, but has these really, really strong hydrogen bonding forces that are holding it together. So the reason that water and oil don't mix is because if they were to mix, you'd have to break all those hydrogen bonds, all those hydrogen bonding forces, And water wouldn't really make good new forces with the oil. So the oil would have to break all its dispersion forces too. So if these were to mix, you'd have oil molecules that could no longer interact with each other. And then you'd have water molecules in between that couldn't interact with the oil molecules very well because they have different types of forces that they want to connect with. So you've broken all those connections, all those nice interactions, all those nice attractions, and you haven't formed any new ones. And so there's no energetic reason to do that. There's nothing stabilizing about that interaction of water with the oil molecules. And so they won't mix, and that's why oil and water don't mix. They'd rather stay connected with their own types of forces in their own layers. That's what we see here. So the oil molecules are stay connected through their dispersion forces, and the water molecules stay connected through their hydrogen bonding. So we can say here when we talk about mixing, only similar types of forces can mix. And we'll talk about solutions a bit later and electrolytes and things like that. Talk about how that works in water a little bit later. All right, so what happens if you do actually want them to mix? So let's say you got a bunch of oil on your hands or grease or something. How do you get it off? You got a couple options. Ready? So you could wash it off with what? Probably need some soap. That would be one way. So how does that work? You know how soap works? I mean, yes, okay, so physically, yes, that's how it works. Do you know how it works at a molecular level? Like why it actually does that? Okay, let's talk about that. A soap molecule is a long carbon-hydrogen chain. So this is all carbon, hydrogen type stuff. And then at the very end, it has some oxygen. And it's actually charged. It actually has a negative charge at the end. It has sodium to balance that out. So what that means is the negative charge side over here is highly polar. And that can interact with water really well because of the negative charge. The negative charge makes it really polar. The other side of it, all this stuff, is nonpolar. And so that can interact with nonpolar stuff really well. So what happens in water when you put soap and water together is all of these soap molecules make these spheres where they have the polar part pointing out and the nonpolar part pointing in. And actually, this is the future, so let's just, right? We are still in the future. Let's just look it up on the internet. Called a micelle. And so that's what I'm trying to draw. You've got the polar part with the O's around the outside, and then all these little tails with the long nonpolar part pointing toward the inside. So nonpolar dirt or oil or whatever can get stuck in the inside. Also bacteria, because all cells have a nonpolar layer on the outside of them. They get stuck on the inside of that, and then water surrounds the outside. And that's how you can kind of make a bridge between the nonpolar stuff you want to wash away and the polar water that you want to wash away with. If you ever like have a bunch of oil on your hands and you try to just wash with water, nothing really happens. It doesn't really come off very well. You put soap in there, and the reason you have to rub it is because the rubbing breaks apart those nonpolar molecules or nonpolar things into small enough particles that they can fit inside these balls called micelles and then be dissolved by the water. So if you see, you'll see these types of things on soaps. I don't know if this one has an ingredient. It doesn't, but things like sodium stearate, sodium lauryl sulfate, those kinds of terms, if you've seen those on soaps and shampoos and things, those are these types of big molecules that can help to get rid of that stuff. All right. A few terms then that we should know, and these will come up again and again, especially as we get into the biological stuff. Hydrophilic is another name for polar, which it literally means like water loving or water or attracted to water, wanting water. It's another way of saying something is polar. So something is hydrophilic, it is something that can dissolve in water. Can dissolve in or mix with water. So what do you think the opposite of that is? Yeah, now confusingly, there's another word that's used for the opposite of hydrophilic. Does anybody know what it is in biological systems usually? Another word for nonpolar stuff that doesn't mix with water. It starts with an L. Ready? Yeah. It's lipophilic. These are nonpolar. Words for nonpolar. Hydrophobic, of course, would mean like afraid of water, but like in chemical terms, it just means doesn't mix with water. The reason that lipophilic also means the same thing is because when we talk about the body, the opposite of the water in the body is the nonpolar parts of the body, which is almost exclusively the fats or fatty areas. And lipid or lipo means fat. So that's not just talking about like the fat in your body, but it also talks about things like the membrane around a cell, which is called the lipid bilayer membrane. And so things, when we talk about things like drug design, drugs have to be designed to be absorbed by the cells, and that's actually kind of tricky because they have to be polar enough to dissolve in all the water in your digestive system and get into your blood, but then non-polar enough to get through that lipid membrane and into the cell. So that's all intermolecular force stuff as well. And we'll probably talk about that a little bit next time. All right, so then the third, or the fourth, I guess, the last term here. Amphiphilic are things that are soluble in polar and nonpolar compounds. So like this soap. Things that would be part polar and part nonpolar. So polar forces tend to go together, nonpolar forces tend to go together. All right, questions about that stuff? Okay, I think that's probably a good place to stop. Let's see. I guess we'll leave that there. So we will do a quiz next Monday on this stuff from today and probably a little bit of review from last from the other stuff too. Wednesday we have, I think there's not a pre-lab for Wednesday. I still have to post the instructions. I'm going to do that right after class, but there's no pre-lab. Don't worry about a pre-lab for Wednesday. Just make sure you read through it, bring your notebook. It's a notebook-based lab where we're going to spend some time planning it and then do it, and then we'll have some time to go through the exam on Wednesday also, providing I get it done. No quiz this week. There's going to be a quiz on Monday next week. All right, well, let me know if you have questions. If you're having trouble with this stuff, come see me. Otherwise, I'll see you Wednesday. Yeah.